Welcome to the Gen AI Research Insight Hub, where we explore graph RAG tutorials. First, let us understand RAG. Normally, an AI like ChatGPT only uses what it was trained on, but with RAG, the AI is connected to our own data such as PDFs, databases, or documents. What is graph RAG? Graph RAG is an advanced form of RAG. Instead of storing data as plain text, we store it as a knowledge graph. So instead of just searching documents, the system can search relationships, understand meaning, and reason over connected data. Let's see the demo first. This is our Medical Graph RAG application. The name of our app is Medical RAG, Clinical Intelligence Portal. What is the use of this app? This app allows us to upload medical datasets, convert them into a knowledge graph, ask clinical questions, get intelligent answers based on relationships between diseases, symptoms, and treatments. Instead of just searching text, this app understands connections between medical concepts. Now let's see how it works, step by step. Now I click on the Upload Data button. This button allows us to upload a medical dataset file into the system. The system will read and process this data to build a medical knowledge graph. Now the File Explorer window opens. Here I select my medical dataset file. This file contains medical information like diseases, symptoms, treatments, and relationships. After selecting the file, I click on the Open button. Now the file is sent to our application for processing. Now you can see the message, Successfully Indexed Large Medical Document Review Data.pdf. This means the document has been read, the data has been converted into embeddings, a knowledge graph has been created, relationships between medical concepts are stored. Now the system is ready to answer clinical questions. Now I type a question. I have fever. This is a simple patient query. Instead of just searching the word fever, the system will check related symptoms, find possible diseases, analyze medical relationships, generate a structured answer. Now we get a detailed medical explanation. The system gives possible causes of fever, related conditions, medical context, structured explanation. This is not just keyword matching. This answer is generated using graph RAG intelligence. Now let us see why graph RAG is needed. Before understanding graph RAG, we must first understand the problem with traditional RAG. Traditional RAG retrieves similar text chunks only. That means it searches based on matching words, not real understanding. It does not understand relationships between concepts. For example, it may know fever and infection, but not how they are connected. It has limited reasoning ability. It cannot think step by step across multiple related concepts. It can produce hallucinated answers. Sometimes it generates information that sounds correct, but is actually wrong. Now we will see how graph RAG works step by step using this diagram. The system works in two major phases. Phase 1, indexing, and Phase 2, query time. In Phase 1, indexing, the system prepares all medical knowledge before any user asks a question. The process starts with medical PDF. This is the source document that contains medical information such as diseases, symptoms, and treatments. Next, the document goes into text chunking. Here, the large PDF is divided into smaller text sections so that it can be processed more efficiently by embedding models and databases. After chunking, the system uses the embedding model, sentence model. This model converts each chunk into numerical vectors called embeddings. These embeddings represent the semantic meaning of the text. At the same time, the system performs entity extraction, NER, medical NER. In this step, important medical entities such as fever, infection, insulin, or diabetes are detected from the text. The embeddings generated earlier are stored inside the vector database, ChromaDB. This database allows semantic similarity search later during query time. The entities extracted from the document are also linked with text chunks and stored again inside the vector database ChromaDB for structured retrieval. Below that, the processed information continues to be stored and organized inside another layer of vector database ChromaDB to ensure all chunks are indexed properly. Finally, at the end of Phase 1, the system is ready and produces medical final answer capability, meaning all document knowledge is now indexed and searchable. At this stage, the system has structured medical entities, vector embeddings, indexed document chunks. Now it is ready for user questions. In Phase 2, query time, the process begins with query embedding, where the user's question such as I have fever is converted into a numerical vector representation. This query vector is then sent to vector retrieval, semantic search, which searches for relevant information inside the vector database, ChromaDB, that stores all embedded document chunks. The retrieved semantic results are prepared for merging in context fusion, vector plus graph. Fused contextual information is then passed to the LLM GFM80M model for grounded answer generation. At the same time, the system also interacts with the knowledge graph Neo4j to access structured medical relationships. From there, it performs KG traversal, which explores connected medical entities such as fever caused by infection. The results of this traversal are again combined in another stage of context fusion, vector plus graph, to ensure both semantic similarity and structured reasoning are integrated. The system may also retrieve structured information from the vector database, Neo4j, as shown in the lower part of the diagram, followed by another refinement step of vector retrieval, semantic search, to strengthen contextual grounding. Finally, after all retrieval and fusion steps are completed, the system produces the medical final answer, which is accurate, context-aware, and generated by the LLM based strictly on the combined vector and graph knowledge. Now let us look at the actual GraphRag project. This is our project folder called GraphRag. Inside it, we have two main parts. Backend. This contains the GraphRag logic. Frontend. This contains the user interface. We will see in Backend folder. This backend folder contains the complete brain of our GraphRag system. Everything related to AI, graph database, vector database, PDF processing, and API lives here. Now we will look at the requirements text file. This file is very important because it tells us what software libraries are needed to build this GraphRag system. These libraries are used to create the API server. In this medical GraphRag application, we use a model called GFM80M. GFM80M is a lightweight generative foundation model that is fast and memory efficient. Fast means quick responses, lightweight means it runs with low compute, and efficient means it works well with documents. In GraphRag, intelligence mainly comes from retrieved PDFs and the medical knowledge graph, not just the model size. This model is loaded locally using Hugging Face transformers, making the system cost-effective. Fast API allows us to create endpoints like /ask and /upload. Uvicorn runs the server. Pydantic validates user input. Python multipart allows file uploads like PDF and CSV. This is how our frontend talks to the GraphRag backend. These are used to connect to external services. Python dotenv reads secret keys from the .m file. Requests is used to call Azure Text-to-Speech. Pandas is used to read medical CSV datasets. This is how thousands of medical questions are loaded into our RAG system. ChromaDB is our vector database. It stores medical text as embeddings so the AI can search by meaning instead of keywords. LangChain OpenAI, LangChain Core. These libraries connect our system to Azure OpenAI. They are used for generating answers, creating embeddings, extracting medical entities from PDFs. Neo4j is the knowledge graph database. This is where we store diseases, symptoms, medicines, relationships like treats or causes. This is what makes our RAG system a GraphRag. PyMu-PDF. It extracts text from PDFs so we can send it to GPT and create the knowledge graph. NumPy helps with vector and embedding calculations behind the scenes. Typing extensions. This helps Python handle modern type hints used in FastAPI and LangChain. Now that we understand how GraphRag works internally, we will see how it is connected to the outside world. This file, called graph-core-rag.py, turns our GraphRag system into a web API that the front end can use. This is what allows users to ask questions in the browser. Let's understand the code. Class Medical GraphRag. This class represents the entire medical GraphRag system. Everything, vector search, PDF processing, graph building, and answering, happens inside this class. Initialize components. Here, the system sets the location of the medical CSV dataset. This file contains thousands of medical questions that will be used for semantic search. ChromaDB. This section creates the vector database. This is where medical text is stored as embeddings, so the system can search by meaning. Create collections. Here, two collections are created, one for medical questions, one for medical documents. If they already exist, they are deleted and recreated to keep the database clean. Embeddings. This section connects to Azure OpenAI to create embeddings. These embeddings convert medical text into numbers, so similarity search becomes possible. Here we connect to the large language model. This is the brain that understands medical text, extracts entities, and writes final answers. Neo4j. This section connects to Neo4j. Neo4j is the knowledge graph database where diseases, symptoms, medicines, and their relationships are stored. Test connection. This part checks whether Neo4j is working correctly. If the connection fails, the system cannot build the medical graph. Medical entity types for knowledge graph. This list defines what kinds of medical things the system understands: disease, symptom, medicine, doctor, test, treatment, and so on. These become the node types in the knowledge graph. Medical relationship types. This list defines how medical things can be connected: treats, causes, has symptom, diagnoses, prescribes, and more. These become the edges in the graph. Initialize Neo4j schema. This runs a setup that creates rules in Neo4j to prevent duplicate diseases, medicines, documents, and chunks. Initialize Neo4j schema. #create constraints for entity uniqueness. This section ensures that every disease, symptom, medicine, and document is stored only once. This keeps the graph clean and reliable. Load default dataset. This loads a medical CSV file containing thousands of questions and answers. After loading, it automatically builds the knowledge base. Enhanced PDF processing with knowledge graph. This is where normal RAG becomes graph RAG. Extract text from PDF. This reads all text from a medical PDF file. Extract medical entities LLM. This sends PDF text to GPT and asks it to extract diseases, symptoms, medicines, and their relationships. The output is structured JSON that graph RAG can understand. Process PDF to graph. This is the most important function in the system. First, it reads the PDF. Then it creates a unique ID so the same PDF is not processed twice. Then it splits the text into chunks. Each chunk is sent to GPT to extract medical entities and relationships. Those entities become nodes. Those relationships become edges. Everything is stored in Neo4j. At the same time, each chunk is also stored in the vector database. Create document node in Neo4j. This creates a main document node that represents the PDF. Process each chunk. Each chunk becomes a graph node, a vector embedding, a source of medical facts. Create document summary. After all chunks are processed, GPT creates a structured summary of the medical document. Graph node creation. Create document node. This stores PDF metadata inside Neo4j. Create chunk node. This stores each text chunk and links it to the document. Create medical entity node. This creates diseases, symptoms, medicines, and other medical entities as graph nodes. Link entity to chunk. This links every entity back to the chunk where it was found. Create medical relationship. This creates relationships like insulin treats diabetes, fever is a symptom of flu. Vector storage. This stores PDF chunks as embeddings so the AI can search them by meaning. Create document summary. This asks GPT to summarize the medical document. Create summary node. This stores that summary in Neo4j and connects it to the document. Ask question. This is where everything comes together. It searches CSV medical data, PDF documents. Uploading data, upload new dataset, allows users to upload new CSV or PDF files. Process CSV, adds new medical questions and rebuilds the vector database. Get statistics, shows how many questions, documents, graph nodes, graph relationship exist in the system. Database control, execute cipher query. This sends commands to Neo4j. Clear database, deletes everything from the knowledge graph. Close, closes the database connections safely. This entire file turns raw medical data into a living, searchable, intelligent medical knowledge graph. That is what makes graph RAG different from normal RAG. This is how graph RAG turns documents into an intelligent medical assistant. Thank you for watching. This is how graph RAG turns data into intelligent answers.